So far, in our electrochemistry unit, we have been considering standard cells, those electrochemical cells that are under conditions of 1 atmospheric pressure and 1 molarity for both of the solutions inside the chemical cell. However, not all conditions are considered standard. Back in our thermodynamics unit, we learned that when we need to calculate the delta G for situations that were not standard, we had to add a correction term to the standard delta G. This usually took into account any variations in temperature that would occur. The equation for that was delta G equals delta G for standard conditions plus the gas constant times temperature in Kelvin times the natural log of the reaction quotient. Now let's remember what each one of these things are. Standard Gibbs free energy. And the gas constant. Now this is kind of weird because you got to make sure that you're using the right units. It's 8.31 joules per mole Kelvin. Temperature in Kelvin. And the Q stands for reaction quotient. Now let's use what we learned in the last video to make this equation useful for electrochemistry. Okay, when we were learning about how thermodynamics works in electrochemistry, we discovered that the delta G, the available work in a system, is equal to negative mole of electrons times Faraday's constant times the electrochemical cell voltage. Okay, so if we substitute this piece of our equation into our thermodynamics equation, we can get something a little bit more useful. So we'll have negative moles of electrons times Faraday's constant times the electrochemical cell voltage should be equal to negative moles of electrons times the Faraday constant times the standard cell potential with this correction factor, the gas constant times temperature times the natural log of the reaction quotient. Okay, that looks pretty nasty. So what we're going to do is we're going to divide all of these terms by negative NF. That way we can kind of simplify where all the letters are in the equation. We'll end up with this really clean looking equation called the Nernst equation. Which is that the electrical cell potential for any electrical cell should be equal to the standard electrical potential minus gas constant times temperature in Kelvin divided by the moles of electrons transferred times Faraday constant times the natural log of the reaction quotient. This equation gives us the power to do some predictive chemistry. Let's say that you had an equation that's really standard in each kind of textbook. In this equation, zinc metal and copper 2 ions will react to form zinc 2+ and copper metals. If we write the reaction quotient for this equation, it's the same technique that we use to write equilibrium expressions. We would say that the Q is equal to the zinc 2+ concentrations divided by the copper 2+ concentrations. Now, to figure out whether your cell potential is going to be greater or less than, by comparing the ratio of the zinc ions to the copper ions, all you really need to know is how logarithms behave and whether they will produce a positive number or a negative number depending on the values that you put inside them. So think for a moment about a logarithmic graph. Here's a rough sketch of a logarithmic graph. Natural log of x versus x. Okay, so I know from math class that this spot right here where the value of the function equals 0 is when we do the natural log of 1. So I know if my ratio of my zinc 2 plus ions to the copper 2 plus ions is greater than 1, that's going to be my spot where my logarithm is positive. Since I know that I have my negative RT over moles of electrons times Faraday constant, natural log of the Q, if I have a positive value for my logarithm, I'm going to be subtracting from my cell potential. So I'm going to have a lower cell potential if my ratio is positive. On the other hand, if the ratio is negative, if we have our zinc 2 plus ions are less in the container than our copper 2 plus ions, that's going to make it so that my logarithm is a negative value. That's going to make two negatives, so it'll be negative times stuff times a negative value, which will be positive, and will add cell potential to my equation. To recap, if you have a reaction quotient value that is greater than 1, your logarithm is going to be positive. This is going to mean you're going to subtract stuff from your cell potential, so your E will be lower than it was before. If you have a value for Q that is less than 1, that's going to make your logarithm negative. And negative times a negative makes a positive. So you're going to be adding values to your cell potential. So your overall new cell potential is going to be higher than it was before. And that's all you really need to know about how to use the Nernst equation.